वेलकम यू ऑल। आज कंटिन्यू करेंगे हम ऑसिलेशंस को। इससे पहले हमने इक्वेशन फॉर द डिस्प्लेसमेंट एंड एक्सेलरेशन एंड वेलोसिटी की इक्वेशन डिराइव की फॉर ए सिंपल हार्मोनिक ऑसिलेटर। आज हम डिराइव करने वाले हैं सिंपल पेंडुलम की इक्वेशन फॉर द टाइम पीरियड ऑफ ए सिंपल पेंडुलम, और ये मोस्टली पूछा जाता है बोर्ड एग्जाम के लिए। तो आज हम इसको डिराइव करने वाले हैं। सिंपल पेंडुलम को हम कैसे डिराइव करते हैं? अगर हम मानते हैं कंसिडर एक सिंपल पेंडुलम है ऑफ लेंथ L, और यहाँ पे वो ये पाइवट पे टाइप किया हुआ है। लेट्स कंसिडर, और यहाँ पे हम सिंपल पेंडुलम का जो मास है विल टेक इज अ पॉइंट मास m, और ये लेंथ ऑफ जो स्ट्रिंग है दैट इज by which it is connected with some pivot. So suppose अगर ये पेंडुलम ऑसिलेट करता है at some angle, say suppose थीटा ये ऑसिलेट करता है मीन पोजीशन से। ऑब्वियसली जब ये पेंडुलम यहाँ पहुँचता है तो यहाँ पे टेंशन की जो डायरेक्शन होगी वो इस तरह होगी। T will be the tension on this string or on this length L of the simple pendulum जो इसके साथ स्ट्रिंग बंधी हुई है, and this will be the mg जो नीचे की तरफ वेट होगा बॉब का। अब जो रेस्टोरिंग फोर्स होगा वो किस डायरेक्शन में होगा? आपको पता ही है कि पेंडुलम रेस्टोर करना चाहेगा। पेंडुलम की टेंडेंसी होती है टू ब्रिंग इटसेल्फ टुवर्ड्स द मीन पोजीशन। तो जो वेट होगा दैट विल बी डाउनवर्ड्स mg। तो यहाँ पे टेंशन इस साइड में है और वेट इस साइड में है, और ये थीटा है। सपोज हम इस mg को रिजॉल्व करने वाले हैं, सपोज विद दिस एंगल थीटा। और जो रेजोल्यूशन होगा इसका mg cos थीटा विल बी इन दिस डायरेक्शन, और वो बैलेंस होगा टेंशन के साथ। एंड mg sin थीटा विल बी along this direction, that is tangentially towards the mean position, जो restoring force होगा। This mg sin theta will behave as a restoring force and it will be towards the mean position, and your object is moving from mean position to extreme position by enhancing its angle. So the acceleration will be towards the mean position. Acceleration is always towards the mean position. So if we take this mg sin theta, this will take this restoring force, F is equal to mg sin theta, और माइनस बिकॉज ये acceleration is towards the mean position। और यहाँ पे हम पेंडुलम का जो oscillation है that will take anti clockwise यहाँ से। If you take it as a positive, तो डिस्प्लेसमेंट यहां की तरफ है तो एक्सेलरेशन विल बी टुवर्ड्स द मीन पोजीशन। और दिस mg का जो ये कंपोनेंट होगा mg sin थीटा, इट विल बिहेव एज द रेस्टोरिंग फोर्स फॉर दिस पेंडुलम टू ब्रिंग इट बैक टुवर्ड्स द मीन पोजीशन। सो यू कैन राइट F is equal to minus mg sin थीटा। सो वी नो हियर थीटा इज टेकन वेरी स्मॉल। आप एंगल बहुत स्मॉल लेते हो, फॉर वेरी स्मॉल एंगल you can take sin theta is equal to theta. So you can write F is equal to minus mg theta. This F is a restoring force. Now we know, let's consider that this pendulum, ये जो pendulum है, it displaces from mean position making an arc x. Suppose this pendulum, when it move from mean position to extreme position, it is moving from mean position to this another position. Say suppose at any instant of time it reached this point while having making the distance traveling the distance x, then x is an arc. So I can use here that angle is equal to theta is equal to arc over a radius. A radius is here L, length L, and theta comes out to be equal to x over L. So I can write F is equal to minus mg x over L. This becomes we are simplifying, we're trying to find out the equation for the time period, or just proving the equation for the time period in case of simple pendulum. So I can write it F by x is equal to mg over L, where L is this length of pendulum, and I take this minus sign here, and we know that F, as we have read in past, F is equal to minus kx, that the force is directly related to the displacement from the mean position, and force is towards the restoring force is towards the mean position, and displacement is away from, displacement means to bring this to take away this pendulum from the mean position. So we can write minus F over x. If I take minus, is equal to k. So instead of F by x minus time, I can write here k. So this comes out to be equal to k is equal to mg over L, or it becomes k by L is equal to k by m is equal to g over L. So when I write k by m is equal to g over L, you know very well that k by m is equal to omega square, already proved k by L. So omega square is equal to g by L. So this implies omega is equal to under root of g by L. This is the equation in terms of omega for the simple pendulum. So we can write it further. So omega comes out to be equal to under root of g by L, and omega has a relation with the time period, that's omega is equal to 2 pi by t. So you can write 2 pi by t is equal to under root of g by L, और t is equal to, यहाँ ले जाएंगे, इसको यहाँ ले जाएंगे, this becomes 2 pi under root of L by g. This is the equation of time period for a simple pendulum. With this pendulum, how much time it will take while going from this to extreme position, then return back towards the left side, left extreme, then return back to the mean position. The time taken to complete one oscillation is called a time period, that is equal to 2 pi under root of L by g. L is the length of pendulum and g is acceleration due to gravity. So this is the proof for the equation of time period in case of a simple pendulum. So you know frequency is equal to reciprocal of time period. So you can find out F is equal to 1 over t, reciprocal of this very value, that means 1 by 2 pi under root of g by L. This is the equation for the frequency. So you can have frequency is equal to 1 over 2 pi under root of g by L. And this is the equation for the time period of a simple pendulum. This is the equation to calculate the frequency of the simple pendulum. This is the proof for the derivation of the equation for the time period and frequency of a simple pendulum. So suppose if I take this pendulum is of length 1 meter, a pendulum of length 1.00 meter, calculate the time period. So how we calculate the time period? So t comes out equal to, you know the formula, t is equal to 2 pi under root of L by g. So you can write T is equal to 2 into 3.14 under root of L is 1, G is 9.8 meter per second square. This is 1.0 meter. So on calculating, you will get 2.01 second. So the time period for a pendulum of length L from is 2 seconds. It will complete its one oscillation, one complete period in a 2 second of time. So this frequency will be equal to 1 by T is equal to F. That will be 1 divided by 2.01, something like that. 49.5 hertz, 45.9 something hertz. This becomes the frequency of this oscillator. Similarly, you can calculate the time period by knowing the length L, because G is constant. The variation in L causes the variation in time period and variation in frequency. And you know that with the variation in G, as we know, and different places, into the depth, at the height, at the surface of Earth, at some polar regions, at equator, the value of G with the rotation, value of G varies, so the time period also vary. So G also here, but somewhere we kept it as the G is constant, but because the change in length causes the change in time period in case of simple pendulum. So this is the equation and this is the numerical. We will go going for the next question in the next session. Thank you very much.